Hi everyone. In this video, we are going to discuss about a mathematical modeling of mechanical system. As you all know that a control system is a collection of components which are connected together to do some objective. The mathematical model of control system constitutes a set of differential equations. That means input and output relationship of the various physical elements or the components of the system is governed by a differential equation. Now this differential equations of a linear time invariant system is considered, and we are going to reshape it in a different form so that we will get a transfer function. We are assuming the system is given with a single input and the system is producing single output. We are introducing a new term called as a transfer function. It is nothing but a Laplace transform of output divided by the Laplace transform of the input. We are assuming zero initial conditions. How can you compute the transfer function means, you know that for this particular control system, you can write the differential equations. If you take the Laplace transform of the differential equations, and we will get the transfer function. Let's see a simple example. You have a motor. In order to rotate the motor, we need to apply the input voltage. So what is the transfer function of this particular system is angular speed to the input voltage ratio. That we will call it as a transfer function of this particular DC motor. You see here, the system is given with an input U of S, output is Y of S. What is the transfer function? Y of S to the U of S. This relationship we will call it as a transfer function. Let's see the mathematical modeling of mechanical system. Generally, we have two types of mechanical system. Mechanical translational system, which I am going to consider this as an MTA, and the mechanical rotational system, we will consider this as an MRA. What is mechanical translational system? Here the motion is in a straight line. Example, a train moving on a track, the car moving forward. We will call it as, even if it is a backward also, it is a translational. It is actually a motion in a straight line. What is a mechanical rotational system means? Here the motion is a circular, that means a rotational path. Example, ceiling fan rotating. It follows a circular path, and the motor shaft rotating is an example of the mechanical rotational system. Let's see the mathematical modeling of mechanical translational system. If you want to model a mechanical translational system, we are using three basic elements such as mass, spring and dashpot. Three elements we are going to use to design or to model a mechanical translational system. Here the weight of the mechanical system is represented by mass. The elastic deformation of the system is represented by spring. If you take a mechanical system, we have a friction that is represented by using a dashpot. You see, this is a mechanical translational system. You are applying a force. Because of that, the system will move in a linear fashion. And for the mechanical system, the sum of force existing on this particular body is zero. Or I can tell a sum of applied force is equal to sum of opposing forces. we'll see a list of symbols used in a modeling of mechanical translational system. As I already told, if you consider the mechanical translational system, if you apply the force as an input, that particular system will move. Here I am representing that as an x, it is a displacement. dx by dt is a velocity, d square x by dt square is an acceleration. And we are using these notations F, Fm, Fk, Fb are actually representing applied force and opposing forces. Mkb are the constants: mass, stiffness of the spring, viscous friction coefficient. You can find these symbols in the modeling of mechanical translational system. Now let us try to write the force balance equation of the three important elements. Let us consider an ideal mass elements. This is the representation of the ideal mass elements, and this particular ideal mass element having negligible friction and elasticity. Let you are going to apply F be the force acting on the particular body. It is represented by the mass. This body or this particular mass will produce some opposing force, which we will call it as an Fm. It is directly proportional to acceleration of the body. Just now we have seen acceleration is represented by d square x by dt square. So Fm is directly proportional to d square x by dt square. This proportionality constant is m. By Newton's second law, I can write sum of applied force is equal to sum of opposing force, which is m into d square x by dt square. Let us consider the second element, dash part. This is a symbol of the dash part. What is basically a dash part is a piston moving inside a cylinder which is filled with viscous fluid. Whenever you apply the force to this dash part will offer an opposing force, which we will call it as an Fb, which is directly proportional to velocity. It is dx by dt, proportionality constant is b. By Newton's second law, applied force is equal to opposing force, b into dx by dt. If you see here, this dash part is connected with a reference point. It is a fixed end. If suppose there is no reference point, then this opposing force is directly proportional to differential velocity. So you have to compute x1 minus x2. So therefore, applied force is equal to opposing force, which is nothing but b d by dt into x1 minus x2, because in this particular dash part we have a displacement at both the ends. The third important element is an ideal spring. You are going to apply the force. This spring will offer an opposing force, which is represented by Fk. Because of this force, the spring will offer an opposing force which is directly proportional to displacement. So it is represented by x, the proportionality constant is k. If suppose there is no reference for this particular spring also, you will have a differential displacement. So it is x1 minus x2. Let's see the mathematical modeling of mechanical rotational system. There are three important elements we are going to use, that is moment of inertia, torsional spring and dash part. The moment of inertia is representing the mass. The elastic deformation is represented by the spring. The friction associated with the mechanical system is represented by dash part. Here you have a system. If you apply the torque, the input is a torque. You are applying the torque. then you will get an angular motion. It is not a linear motion. For a rotational system, sum of applied torque acting on a body is 0. That means sum of applied torque is equal to sum of opposing torques. These are the symbols which we are going to use in a mechanical rotational system. Instead of x, we are using a theta. We are having an angular displacement. Likewise, angular displacement. So here, instead of the force balance equation, we are writing a torque balance equation because the input is a torque. This is the symbol of ideal mass element. It is the represented by J in case of MRS. You are going to apply the torque, because of that it will rotate. It will produce some opposing torque which is directly proportional to angular acceleration. So because of that we are having theta term, J into d square theta by dt square. This is applied torque is equal to opposing torque. This is for the dash part. Opposing torque is directly proportional to angular velocity. So it is theta instead of x. And if we are having the displacement at both the ends, theta 1 and theta 2, we have to find the differential angular velocity. And this is for the ideal spring. The same thing, you are applying the torque. Because of that you will have an opposing torque which is offered by the spring, which is directly proportional to angular displacement. It is T is equal to Tk, which is nothing but k into theta. If we are removing this reference, you will have a differential displacement at both the ends. So it is theta 1 minus theta 2. These are the references. Thank you.